Good morning, everyone. My name is Kato, and I'm from CMU. And once again, I'm going to talk about TimeGraph, which is an approach to GPU scheduling for real-time multitasking environments. So as you may have noticed in recent years, the graphics applications have significantly improved our user experience, right? So for instance, 3D games, 3D windows, 3D interfaces are becoming more and more popular and commonplace. And I believe that this graphics improvement will continue to go through innovations in the graphics processing unit, so-called GPU. So what is GPU? So GPU is highly parallel architecture. So for example, NVIDIA's GPU integrates about 500 cores on a chip, and it is very suitable to support data parallel and compute-intensive applications, such as image processing, right? Because a large amount of data can be computed simultaneously by these many cores. And if you look at the performance trends today, the GPU is actually more than 10 times faster than the CPU today in peak performance, right? And this performance benefit of the GPU over the CPU is continuously growing. And also, GPU is of significant impact over the CPU in performance per watt, which means GPU is very energy efficient. So in fact, it is about 7 times more energy efficient than the CPU today. And this energy efficiency of the GPU is also continuously growing. And furthermore, it is not just only graphics, but also many applications can use the benefit of the GPU thanks to the recent advancement of programming technology, also known as GPU. So GPU is obviously attractive in performance, but we are given a problem to address, particularly in multitasking environments. So this problem is actually attributed to the fact that the GPU is command-driven. So there are multiple different cases where GPU commands are used. So specifically, the CPU has to send the GPU command to the GPU to upload the GPU code from the host memory to device memory. And similarly, we also have to use the same kind of command to copy the data from host memory to device memory, which is to be used for the computation, right? And to start GPU code on the GPU, again, we have to send another command to the GPU. And GPU execution usually outputs some data, right, because it's computing something. Then, which means we have to send another command again to copy this output data back onto the host memory. So GPU is a command-driven. And this command-driven model actually makes multitasking very difficult for the GPU. So let's consider 2 tasks with different priorities for simplicity of the example. A task sends a GPU command to the GPU to use the GPU. And if the GPU is idle at this moment, then there is no problem. The GPU context can start execution immediately. However, if the GPU is not idle when tasks send the GPU commands, then their requests need to wait and will be dispatched later when the GPU gets idle. So the major problem, which we can see herein, is that the GPU itself dispatches these GPU commands in their arrival order. So which means if the low priority tasks send many GPU commands to the GPU, the high priority task could be blocked for a long time on the GPU. Maybe long or maybe short, right? Depends on what kind of data we're transferring. For instance, if you want to copy large data from host memory to the device memory, then blocking time will be very huge. And as a result, the high priority task may be blocked for a long time on the GPU. So the graph shows briefly the impact of performance interference that the foreground 3D games received from different types of GPU applications running in the background. So this is kind of preliminary experiment which we provided. So the decrease in performance of the 3D game actually depends on competing workloads. So as you can see, so it can easily become unresponsive if the competing workload is high. And such a performance interference occurs even for different GPUs, right? Different types of GPUs, and also for different types of device drivers, which means, so this is a fundamental problem we have to address to use the GPU multitasking environments. So next I'm going to present our solution, TimeGraph, to address the aforementioned multitasking problem on the GPU. So TimeGraph is a GPU scheduler implemented in the device driver running on the CPU. And any GPU command groups or any GPU commands coming to the device driver from user space are preempted by TimeGraph to make them wait in a queue. And TimeGraph always dispatches the GPU commands of the high priority task, which is waiting in this queue, to the device driver. And this device driver just submits this command to the GPU. And when the GPU command, GPU context execution finishes, the TimeGraph also configures the GPU to generate an interrupt to the CPU from the GPU, so that TimeGraph itself can be notified of the completion of the preceding GPU context execution. And upon this notification, the TimeGraph can dispatch the next GPU command to the GPU. So this is an entire mechanism in TimeGraph about how to schedule GPU commands. So again, this is the scheduling of GPU commands. It doesn't schedule the GPU context itself. So TimeGraph supports two scheduling policies. And let's first look into the predictable response time policy. So let's consider two tasks with different priorities again, kind of similar example as before. And if the GPU is idle, a task just can't use the GPU, like the previous case. But if the GPU is not idle, the GPU command must be enqueued in the TimeGraph space, like this. And at some later point of time, when the previous context finishes, the current context finishes, the GPU is configured to generate an interrupt to the CPU, and the scheduler, TimeGraph scheduler, is invoked to dispatch the next GPU command according to the corresponding task's priorities. Right, in this case, the high priority task can take over the low priority task. And as a result, GPU context executions are correctly prioritized. However, the scheduling overhead appears because the TimeGraph scheduler needs to be invoked at every GPU context switching. And in order to reduce this scheduling overhead, TimeGraph supports another scheduling policy, which is called the high throughput policy. So this policy actually modifies the aforementioned predictable response time policy to enqueue the GPU commands only if their priority is lower than the current GPU context. So for example, we do not really have to enqueue the GPU commands of the high priority task because at this moment, the current GPU context is at the same priority level as the incoming GPU command. So instead, this GPU command can bypass the queuing. And hence, the scheduling overhead is reduced, right? Because there is no need to invoke the scheduler to schedule GPU commands. But meanwhile, some overhead still remains when switching to different priority levels, right? From high priority task to low priority task if the context is switched, still we need to invoke the GPU scheduler. And furthermore, the time graph also supports GPU reservation functions to ensure the GPU resource usage not to be overutilized. So there are two reservation policies again supported. And let's look into the first policy, posterior enforcement. So according to this reservation policy, the execution budget is initialized to the specified capacity set by system designers. And let's assume that in this case, the high priority task has a reservation and low priority task doesn't have. The budget is, so it's initialized to the specified capacity at the first. And this budget is decreased by the same amount of time consumed by the corresponding task on the GPU. So this is exactly the same as the traditional resource reservation schemes. And please notice that GPU commands need to be scheduled under the predictable response time policy. So you shouldn't use the high throughput policy in this case if you want to use the GPU reservations. And according to this posterior enforcement policy, the task can use the GPU if the budget is greater than 0 when submitting the GPU command. However, once it becomes negative, once the budget becomes negative, the task is forced to wait in a queue, even though it has the highest priority. And instead, the low priority task can use the GPU. So the budget is replenished at the specified period set by system designers. Then once it becomes the sufficient amount, the corresponding high priority task can use the GPU again. So there is another policy supported in TimeGraph is a priori enforcement. So the previous policy, so you can see that this is quite optimistic because the budget can be negative, right? So it may somehow overutilize the GPU. So in order to make it more pessimistically, so we provide another reservation policy called a priori enforcement, which tries to enforce a task execution before submitting the GPU command rather than after submitting the GPU command. So more precisely, TimeGraph predicts the GPU execution time before the GPU command is submitted to the GPU. And if the GPU context execution is verified not to cause the budget to be negative, then the task can use the GPU. But however, if the prediction detects that this execution would cause the budget to be negative by prediction, then the corresponding GPU command is forced to wait, even though it has the highest priority. Right. So even though it has the highest priority, it is enforced not to go to the GPU. And thus this policy is more pessimistic because the budget may be left unused. And so the question here is, how do we predict the execution time, GPU execution time? And this is quite interesting, but very difficult problem to solve. So in this paper, we used a history-based approach where we just search the records of previous sequences of the GPU command that match the incoming sequences of the GPU commands, right? This actually works for 2D programs because the GPU command itself does something on the GPU. But for compute or 3D, the GPU command just launches something, right? Launches something stored on host memory, which may be very long GPU kernel execution, or which may be very long data copy operation. So we can't predict here. In this case, the prediction may or may not work. So which is we have to look into the solution more carefully in the future work. So for the details, please see our paper about how to predict the GPU execution time in TimeGraph. Now I'm going to show some evaluation and experimental results, which we provided in this paper. So we implemented TimeGraph in the Nouveau open source Linux driver. So this is actually already included in the main line of the Linux kernel. And the benchmark programs are selected from the USENIX test suite and the Gallium demo kit. So if you're interested in these benchmark programs, please visit the websites there. So this graph shows the frame rate of 3D games when graphics bomb, which is some graphics application that keeps sending so many GPU commands to overload the GPU. So tries to kill the GPU. So this kind of graphics bomb application is running in the background. And if TimeGraph is not used, the games become, as you can see, nearly unresponsive because it's affected so much by this graphics bomb. On the other hand, if you assign high priority to these games through TimeGraph functions, then their frame rate is significantly improved. And furthermore, by limiting the GPU resource usage of the background graphics bomb to 10% through GPU reservation functions of TimeGraph, then you can see that the frame rates of 3D games are more successfully protected from performance interference. And using a prior enforcement, furthermore, for graphics bomb, right? So the previous case is just a posterior enforcement, which tries to block the execution of graphics bomb after they submit the GPU. But if we try to block the execution of graphics bomb before they send the GPU commands, then you can furthermore protect the activity of important application, in this case, 3D games, right? Next, let's see the performance interference on the time. So these graphs show that the frame rates of 3 instances of some kind of lightweight 3D widget tasks when competing with each other. So without TimeGraph support, their frame rates are clearly messed up, right? Well, somehow they prioritize because we still use CPU priorities. So if you prioritize the activities of GPU applications on CPU, it somehow works, right? Still, for instance, let the widget number 1 task has a still priority, but basically it is messed up. But on the other hand, if you use the priority support from TimeGraph, it can correctly prioritize the 3 tasks, right? But in this case, the low priority task, the lowest priority task, doesn't get GPU resources at all because it doesn't get GPU resources because of its priority. Instead, reservation support of TimeGraph, if you assign the GPU resource of these tasks correctly, then you can make them executing at the specified rate, at the desired rate from the perspective of systems designer, very stably, right, on the time. So if you use the reservation, then you can provide very stable execution for the GPU applications. So TimeGraph is quite beneficial, we believe, but overhead is inevitably imposed due to the scheduling process. In particular, the more functions are used by TimeGraph, such as reservations with predictions, then the more overhead is imposed inevitably, like you can see by the orange graph, right? So it's more like about 50% of overhead must be imposed if you want to really strictly block the execution of competing workload. But we believe that this overhead is acceptable for protecting the GPU from performance interference, right? Because if you do not use this function, then your important applications is anyway killed. So this overhead, we believe, is very acceptable. Okay, so I summarize this talk. So we presented TimeGraph, which enables prioritization and isolation for GPU applications in real-time multitasking environments. And this is a device driver solution, so which means you don't have to apply any modification to user space. You can just use the existing library, compiler, and so on. And which provides the scheduling concepts of GPU commands. Again, this is scheduling of GPU commands. It doesn't try to schedule the GPU context itself, right? So it tries to control the GPU from the CPU side. And it also provides the reservation concepts for the GPU applications. And this is open source software, and you can download from our website if you're interested in. But unfortunately, recently, the disk is quite damaged, and currently, our website is getting trying to get recovered. So please visit later once it becomes available. And we have kept working on this project, and there was quite significant progress from the time when we submitted this paper. So the current status is actually GPU is supported, right? So this presentation, I only provided the graphics workloads, right, in evaluation. But actually, our TimeGraph scheme can be used for GPU. And this was enabled thanks to the support from Pascal Corporation. So we're actually developing another device driver because Nouveau in Linux, it's developed for graphics, and it cannot be used for compute GPU applications for now. So we actually switched from Nouveau to another device driver, which we developed from scratch. And we're also trying to make open source fast and reliable, which means actually we are happy to announce that our open source driver is getting very competitive to the proprietary driver from NVIDIA, which is closed source. And some results you can see from our OSPAT paper, which will appear in the next months. And you can see, so this is a simple preliminary evaluation for matrix multiplication. And if you compare our open source driver and NVIDIA's closed source proprietary driver, you don't really see the performance difference. Actually, the performance difference is limited only to 10%. So which means I think we are ready to use this kind of open source software stack for the research community. And if you are interested in these open source solutions, please visit our paper, which is currently available online. That's it. Thank you very much.
Questions?
Hi, this is Ali from VMware. I was wondering, have you considered the effects of the memory management scheduling versus your CPU scheduling? And what are you looking at in there?
Yes, actually, yes, we are working on the memory copy scheduling, right? So the memory matter falls into two approaches. One, you have to also schedule when you copy the data from host memory to device memory. And another problem is how do you actually assign the memory space. So there are two separate problems, and we are working on the scheduling problem, which the paper is currently under submission, but hopefully it will appear at some conference. So you can actually schedule in the same manner as TimeGraph. So when you copy the data from host memory to device memory, you have to send the GPU command anyway. So you can actually catch this GPU command in the device driver space. So you can enqueue the command to the GPU driver, but you have to tell, hey, this is a GPU command to copy the data. Otherwise, the TimeGraph tries to queue every GPU command. So maybe there should be some improvement to coordinate between the device driver and user space library so that the user space can tell the GPU driver which commands to enqueue. So for instance, memory copy GPU command should be enqueued to schedule or something. But clearly, it's possible to schedule the memory copy.
Thanks.
On the CPU.
Kai Shen from the University of Rochester. I like this work very much. Is the source code currently available online?
Yes, the time graph is currently implemented in Nouveau, and the website is just currently down due to the damage of disk, but it will be available shortly. Then you can download the source code of TimeGraph. But this TimeGraph implementation is applied for Nouveau, so which means you cannot use this TimeGraph implementation for compute GPU.
I understand. Okay.
But yes.
My question following up to this is that, so your mechanism, your scheduling mechanism sort of instruments the device driver,
yes,
which makes it not feasible for a closed source driver. I want to sort of understand, if you can, using very simple words, why it is not possible to apply this kind of scheduling mechanism somewhere on top of device drivers so that you don't have to change it. Is there any simple reason why that wouldn't be possible?
Two reasons. First of all, runtime library is also closed source, so you cannot actually modify the source code, while we provide open source library even from scratch because we developed it from scratch. But basically, you can't implement your idea in runtime because it is closed source. It has been closed source. The other reason is if you try to schedule something in user space, then the problem is reduced to the problem of user thread vs kernel thread scheduling problems, right? So if you schedule in user space, then you get more preemptions. But if you schedule in kernel space, then you can actually control when it is preempted or not. So the scheduler doesn't want to get preempted when performing the schedulers, right? So user space implementation inevitably incurs some overhead in performance. But you can definitely implement the scheduler in user space on top of device drivers. Instead, you need to compromise the performance.
Thank you. Can I just follow up with another quick one? Have you thought about coordinating the GPU scheduling with CPU scheduling?
That's a very interesting problem, which if you visit our OSPAT paper, then we briefly provide some ideas about how we should coordinate the CPU scheduling and the GPU scheduling. But this is definitely a very interesting problem to solve.
Thank you. Hi, Björn Döbel to Dresden. As you're doing sometimes, make conservative assumptions about reservations, could this lead to situations where you're actually not utilizing the GPU in a way you could if you just send all the commands directly to the GPU? And do you see this as a problem actually? And do you have any ideas how to solve that?
Can you repeat it again, the first part, because I couldn't hear?
Do you see it that there is a problem with maybe not utilizing the GPU completely by making reservations, which then are not used by the one you're making the reservations for, and you could schedule other GPU commands or command groups in between?
Oh, I see, yes. I guess that's possible, but I guess implementation is very challenging, right? Because the GPU scheduler, in this sense, TimeGraph, is a kernel thread. So while it is executing, it can just do its scheduling.
Yeah, my question was more aiming at the point whether you think this is a problem at all, or
oh, I see.
From your experience.
From my experience, it wouldn't be a problem. From my experience, but we need to investigation, I guess, to show really it is not a problem.
Thank you.
We have time for one more question.
Okay. The predictor part of your scheme.
Particular part of, I'm sorry?
The predictor part. Predictor. The prediction of the. Yeah. This is well known to be a very hard problem where you can very easily go into wrong predictions. So can you comment about the way you predict and also about if the predictor does not achieve good results, what's the impact on the overall scheme?
Yes. Actually, from my experience, I don't recommend to predict at runtime. But if you have some coordination between user space and kernel space, then because user space has compiler or runtime engines which compiles the program in real time, so it can provide some information about GPU context to the device level, which I believe is more straightforward. So because the kernel GPU driver doesn't have to predict the GPU execution time at runtime because it's quite of overhead, right? So our approach in the future work would be to provide some coordination between user space and kernel space so that the user space can give the information to the kernel space.
Okay.
Thank you very much.